Hi, in this section we'll take a look at the neat little trick or a technique that we'll use to integrate certain functions via U-substitution. So if we recall chain rule, let's say the derivative of a composite function, if you recall it's the derivative of the outside function, f prime of g of x times g prime of x. If we take that and we work backwards, so we need to have an integral of a function in this form, f prime of g of x times g prime of x. If then we can identify the g of x, typically the inside function, as the u, and perform the substitution. So I'll show you how the technique works, and so you can actually integrate the function, and then there are certain shortcuts that work almost exactly the same. I mean, it's really the same process, just without using the u. So let's say if we have this example, integral of 2x cubed plus 1 to the 4th power times 6x squared dx. Typically would have been a difficult integral to integrate directly because of the 4th power and the multiplication and so on, but here's how we can perform the u substitution. Let's take a look at the inside function and call this u. If you notice, I highlighted it. So if we call this u, which is 2x cubed plus 1, then what we can do is find the derivative of that u, which is 6x squared. And notice how there is a 6x squared within the integral. So that means we will be able to use this technique. So if this is how we call it, du over dx, because this is a derivative of u with respect to x. If we multiply both sides by dx, because we need to match the substitution exactly. This is the way I do it. I know in class some of you do this a little bit differently, but I prefer to start with all x's and turn them into all u. And so how do we do this? So again, start with a u, take the derivative of it. Sometimes we'll multiply by dx. I think this is the first time I'm going to do it. And a little bit later, I'll just call this du equals to take the derivative and multiply by dx. And then let's perform the substitution. So notice it's still an integral. And 2x cubed plus 1 was u. So it becomes u to the 4th power. 6x squared times dx was du, if you notice up above. So it basically becomes u to the 4th times du. And that's a rather simple integral to do using the power rule from previous section. So if you note, as soon as you turn it into u, then you can integrate. What's the antiderivative of u to the 4th? Well, it's u to the 5th over 5 plus a constant. And again, as soon as we integrate, the integral sign is gone, the du is gone, so we just get the antiderivative plus a constant. And at the very end, we back substitute for the u, which was 2x cubed plus 1 to the 5th power over 5 plus c. And that's the final answer. So it's great when it matches exactly, because then you can just substitute, but it rarely does. In fact, most of the time it does not. But the only difference should be is a constant. So let's take a look at this one real quick. What if we have an integral of 3x minus 5 to the 3rd power times dx? Again, note, we can use the inside function as the u, which is 3x minus 5. Take the derivative of u, which is du, equals to, it's 3, and then times the dx at the end. We always attach the dx. Notice there is no 3 outside of parentheses, so the inside function does not count, but there is no 3 outside of it. So what do we have to do? Typically what I do is divide both sides by 3, so we get 1/3 du equals to dx. And again, now we can substitute. So what do we do to perform the substitution? Again, 3x minus 5 becomes u to the 3rd power. And what was dx? If you know, dx is equal to 1/3 times du. So I'm going to put 1/3 times du right here. So again, we're just swapping it out to substitute one thing for the other. And now we just have the u. 1/3 is just a constant. So you can take it outside of the integral, or basically I just took it outside and then I took the antiderivative of u to the 3rd, which becomes u to the 4 over 4 plus a constant. And to simplify it out, we can multiply it and substitute back. So you'll notice it's u to the 4 over 12 plus a constant, which is 3x minus 5 to the 4 over 12 plus a constant. And that's it. So the process is always the same. We can try the same thing with e. Now, if you have e, if you recall with chain rule, usually the inside function is the exponent. Let's call it x over 2. So u equals x over 2. What is the derivative? That's du equals to derivative of x over 2 is basically a half, or 1 over 2. And then times dx. Don't forget to multiply by dx. Then the problem is we have dx, we do not have a half. So here, instead of dividing by a half, it's really the same thing as multiplying by 2. So I multiply both sides by 2 to get just the dx. So you'll notice dx equals to 2 du. And then we substitute. If you recall, it was integral e. Instead of x over 2, we're going to write u times the dx is twice the du. So again, we divide it by half, or it's the same thing as multiplying by 2. So it's 2 du. Then, again, 2 is a constant. We'll pull it in the front. And then what's the antiderivative of e to the u? Well, it's usually the same thing, which it is in this case. It's e to the u plus a constant. And at the end, we substitute back. So it's 2 e to the x over 2 plus a constant. Okay, so it basically works the same way with the e. Let's take a look at one more. What if I have integral? This one's a little bit more complicated, but it looks like x plus 1 in parentheses times e to the x plus 1 squared power dx. Again, what do we call u? I'm going to call the whole exponent, which is x plus 1 squared. You don't want to just do x plus 1 because then you'll get e to the u squared, and then you'll have basically similar problem as far as integrating. So we'll just call the whole exponent as the u. How do we take derivative? If you recall chain rule, 2 comes down, x plus 1, and then times 1, which I didn't put, but it's there, and then times dx at the end. So always attach the dx. And again, we have the x plus 1, we have the dx, even though they're separated, they're still multiplied, but we do not have the 2. So what do? We can divide both sides by 2. So I'm getting a half d times du equals to, still parentheses, x plus 1 times dx. Now we are ready to substitute. So when we substitute, again, we keep the integral. The x plus 1, it just depends on how you like to substitute it, but I like to just typically substitute one thing for the other. So if I can write on here, so basically x plus 1 gets matched with a half. So instead of x plus 1, I'm going to put 1/2. I'm going to keep the e. The exponent becomes the u by design, times, and then the dx becomes the du. So that gets matched with the du. So everything is in terms of u. So constants on the front, which is a little bit cleaner than having it on the back. Some of you may just want to write this 1/2 times du at the end, which is fine too. And then how do you integrate it? Again, a half is a constant, e to the u stays, and then it becomes 1/2 e to the x plus 1 squared plus c. So again, a similarly complicated integral was made much easier via this substitution. So here we'll do one more before maybe we do the little shortcut introduction. So what if it was 3x plus 1 to the 5th power times dx? We've done this one in class. So again, you take the u as 3x plus 1. What is du? It's the derivative. It's 3 times dx. Divide by 3. And then we substitute. So what do we get? 3x plus 1 becomes u to the 5th power times the dx is equal to 1/3 times du. So I'm attaching it at the end. And so again, 1/3 comes out, and it becomes u to the 6 over 6. So it becomes u to the 6 over 18. And it becomes, then we substitute back to get the final answer. And now, these are some kind of interesting shortcuts. So you'll notice it's really the same kind of idea. If you notice, if you have a linear function, let's say of the form ax plus b to the n power, then 1 over a, how do we get 1 over a? Well, first of all, it's a constant in front of x, but you can also think of it as the derivative of ax plus b. Derivative of ax is a, the b is just constant, so it's 0. So we'll get 1 over the derivative, which is 1 over 3 in the previous example. And then you just integrate ax plus b, so it becomes to the n plus 1 power over n plus 1 plus a constant. And if you do the one above it, it's really the same thing. If you notice, this is the example, 3x plus 1 to the 5th power. Well, it's times 1 over the derivative, which is 3, which is the same thing when we divide by 3 with a du. You know, it's really the same kind of process. And then it becomes 3x plus 1 to the 6th power over 6. and then we get the same answer as above. So notice it's quicker. It's a little bit harder to see why that is, but if you've done U substitution a few times, you will definitely see why. It's again same process when you divide to match the du. The e works the same way. It's 1 over the derivative times e stays the same. We do not actually alter the exponent in any way. We do not change it. And so we get same thing with the e. And notice how you see some of the similar examples. We've done this one in class. Again, we can do this with a shortcut. What is the derivative of negative x minus 1? It's negative 1. If you remember, dividing by negative 1 is the same thing as multiplying by negative 1. And then you just integrate it, so it becomes negative x minus 1 to the 8th power over 8 plus a constant. So again, here we just use the shortcut. We can try the same thing with in here. Even though there is a constant 1.2, we can just bring it down. Then it's 1 over the derivative of 0.6x plus 2. Becomes basically 1 over 0.6 times e to the same exponent, 0.6x plus 2. And here we can simplify 1.2 divided by 0.6, so we just get 2 as the final answer with the rest. Now, I've mentioned this also, something similar with e dividing by the constant in the previous section, so you'll see this again. So here is somewhat more complicated examples. So I say with the square root, but you have 3x times the square root of negative x squared plus 1. Again, we can rewrite it as a half power right off the bat. Make u as the inside function. Again, take the derivative, which is du, equals to negative 2x dx. Again, we have 3x here, but we have negative 2x here. So what do? We divide by negative 2. So I'm getting negative half du equals to x times dx. And then we substitute back. The 3 actually doesn't go anywhere, so it stays. Again, I like to match them a little bit. Again, see if I can write this. So x gets matched with a negative half. So instead of the x, I'm putting negative half. And then it becomes u to the 1/2 power, and then dx becomes du. Or you could have kept it at the end. It's really the same thing. And 3 times negative half is negative 3 over 2, u to the 1/2 power du. And then we integrate. So it becomes negative 3/2 stays times. If you add 1 to the 1/2, you'll get 3 over 2, and we divide by it. So notice we can also flip it to multiply, and we cancel pretty much the 3/2 with 2/3, so you will just get the negative u to the 3/2 power. And then we substitute back to get the final answer. Okay, and similarly, this is the one more example with the e. What if we have 2x minus 1 times e to the 2x squared minus 2x? Again, make the whole exponent equal to u. Take the derivative. So that's 4x minus 2 times dx in parentheses because it's more than one term. But notice it doesn't really match, so I pulled out a 2. And to get it to match, we divide by 2 because, again, there is no constant 2 outside of the derivative. So then we get 1/2 instead of 2x minus 1 e to the u power times du. Because there was 2x minus 1 dx equals to 1/2 du. Again, you can either separate them or keep them together. And then you integrate it, and you basically get 1/2 e to the 2x squared minus 2x plus c. So that's the u substitution. There is an actually interesting shortcut that was discussed. Again, it's in that section if you read it in the book. I think page 475, I believe. I know it's at the very end. That you can use this shortcut if you keep the whatever you're multiplying by, let's say 2x minus 1. Then you divide by the derivative, in this case of the exponent, just like you did with the e with a constant, which is 4x minus 2. And then multiplied by the antiderivative, which is for the e is basically itself, always the easy one, plus c. It looks complicated, but notice if you pull out 2 in the bottom, I'll see if I can squeeze this in. Let me actually write over here, equals to 2x minus 1 over, and I skipped the parentheses because we don't actually need them, 2 divided by 2x minus 1. And the thing is, the x's should cancel. and then times e to the 2x squared minus 2x plus c. And so you'll notice the answer would actually be 1/2. This is how we get it right here also. And then e to the 2x squared minus 2x plus c. So it's kind of neat. So again, you pull out whatever you're multiplying divided by the derivative and make sure it cancels out. And that's kind of the shortcut. And the same thing you could have actually done with a radical. You can also do this. So it's actually 3x divided by the derivative of negative x squared plus 1, which is negative 2x. And then times, and then you integrate. So it's actually negative x squared plus 1. You still have to integrate the 1/2. So it's 3/2 over 3/2 plus c. And again, the x cancels. But that's how come we get the negative 3/2. We don't actually get it in the final answer because when you multiply by the denominator, you flip it. And that becomes negative x squared plus 1 to the 3/2 power plus c, and you'll notice same thing, these go away, so you actually get same exact answer. So it's a neat looking shortcut, but I really recommend practicing the U-substitution because it helps you understand what's happening there. And that's it for this section.